Students, in this video, I'm going to give a small introduction about joint probability distribution. So far, we have discussed probability distributions associated with a single random variable. The same can be generalized for two or more random variables. We discuss probability distributions based on two random variables referred to as joint distributions. Basically, joint probability is a measure of two events happening at the same time. First, let us know what is joint probability function in the case of discrete random variables. So, joint probability function is P referred to as P of x comma y, that can be written as P equal to x equal to x, y equal to y. Earlier you have written in the if it is based on single random variable, so we have written it is P of x equal to 1 is P of 1. Same way, this is based on two random variables. And condition for discrete probability function are it is joint probability mass function. Same like earlier you are known every probability function value should be greater than or equal to 0. Same way, first condition is probability function for two random variable, it should be greater than or equal to 0. The second condition is double summation 1 for x, 1 for y. So P of x comma y equal to 1. So this can be simple way you can write double summation. Just you can write P of x comma y is equal to 1. So let us see what is joint distribution table. Understanding the table, we can solve the problem easily. X values are given vertically. So suppose x is x1, x2, generally xm. Similarly, y values are y1, y2, continuing yn. Okay. So these are we have to fill. These are probabilities for correspondingly x1 y1, x1 y2, x1 yn, and then x2 y1, like that. Those are denoted by p11, nothing but probability for the random variable x1 and y1. Similarly, p12 probability for the random value x1 y2. So continuing like this, we can fill like this P1n. So P21, P22, P2n, PM1, PM2, PMN. These are the probabilities for corresponding random variables x and y. Now adding row wise P11 plus P12 plus P1n. So adding row wise, this is filled as Px1. So this Px1 is probability for the corresponding random variable x1. So what is that? It is P11 plus P12 plus P13 and so on, row wise. This all equal to P of x1. Similarly, this can be written as P of x2. So adding row wise, we get probability for the random variable x values. Similarly, adding vertically column wise. So that is P11 plus P21, you can observe here, and so on, equal to P of y1. So that is here P of y1. Adding vertically P of y2. P of yn. This is P of x m. Finally, adding P of x1 to P of xm is equal to P of y1 to P of ym n. This must be equal to 1. So this must be 1. This is called joint distribution table. For example, Considering the experiment of tossing coin twice, the sample space is 2 times head, then tail, then first tail, then head, then 2 times tail. The random variables we define, suppose x is a number of heads obtaining in first toss and y is the number of heads in the second toss. So x is number of head in first toss 1 1 0 0. Y is number of head in second toss. So 1 0. Here second toss is head 1 0. So this is how to what is joint distribution. It is a chance of two events happening at a time. Now, how to define for this joint distribution? So we have to note down the values like this. Y values horizontally, x values vertically. That is range. X values range is 0, 1. Y value range is 0, 1. So we have noted that. Then this probability, this probability is what? Obtaining probability for x is 0, y is 0. So where you are getting the last chance. So this is 0, 0 means obtaining head is first, no at first, no at second. That's a probability. We are having one time of that. So 0 0, that out of 4 possibilities, so that probability is 1 by 4. Similarly 0 1 0 1 0 1 we have out of 4, it is 1 by 4. Similarly 1 comma 0 also one time out of 4, 1 and 1 also one time out of 4. So let us add this. 1 by 4 plus 1 by 4 is 1 by 2. Similarly this is 1 by 2, this is 1 by 2, vertically adding, this is 1 by 2. So vertically or horizontally, last row last column gives the summation 1. So that is what joint distribution. Next, marginal probability distribution. So marginal distribution of x. So noting down x is x1, x2, so on xm, and correspondingly probability function. This is obtained from the table, joint distribution table. Adding row wise, you have calculated p11 plus p12 plus like that. So that is the marginal distribution of M. Then similarly y, we know down y1, y2, so on yn. So probability function from the joint distribution table, last row. This is a last column. This is a last row. So that is py1, py2, and so on pyn. So these two are called joint marginal distributions of x and y. So next, independent random variables. You know already when two events are independent, so we write like this. My probability of A and B, A intersection B is equal to probability of A into probability of B. So when joint distribution, two variables are independent, when P of x comma y, you can write simply like this, P of x comma y is equal to P of x into P of y. So some important formulas you need to remember. Expectation of function. It can be h of x is some function. It's a single function variable. So that's why single summation h of x into probability function. If it is you are finding expectation of two variable function, so double summation h of x comma y pij. So we have in our one important formula expectation of xy, that is a double summation. So h of x comma y nothing but xy xi yj, means it will vary. One summation vary for x, one summation vary for j. Then probabilities. For example, this equal to x1 y1 p11, x1 y2 p12. Like this, based upon the values how many we have, it will continue. Then covariance is defined by expectation of xy minus expectation of x into expectation of y, or you can also call this as expectation of xy is mean x into mean y, because mean of x is equal to expectation of x, mean of y equal to expectation of y. Then finally, the correlation of x and y is defined by rho. So it's a covariance divided by standard deviation. You know all this standard deviation how to find. That's a square root of variance.